Hello, everybody. This is Mr. Gasca. We're going to be looking at Unit 3 for response questions. So we're going to be looking at the circular motion, how to draw free body diagrams for those, and answer a pair of questions that might appear in a similar vein on the AP exam if they are asked. So it reads, in the apparatus shown above, one end of the string of length L is attached to a block of mass M, and the other end is connected to the axle of a motor that rotates, causing the block to move in a circle of radius r at a constant speed vt, such that the string makes an angle with a vertical. The student wants to use the apparatus to make measurements and create a graph that can be used to estimate the acceleration due to gravity at the surface of the Earth. The student can adjust the motor to achieve different tangential speeds of the block. On the dot below, the dot below represents the object as it travels in a horizontal surface at a constant tangential speed at the position shown in the figure above. On the dot, draw and label the forces, not components, exerted on the object. Each force must be represented by a distinct arrow starting on and pointing away from the dot. But we're going to draw a free body diagram on this dot here. One of the important things to remember is for the AP exam, if you have to draw a free body diagram, you're going to want your arrows to be nice and neat, and you are allowed a straight edge on the exam. So I would definitely take one with me, like a ruler of sorts, not protractors. Protractors are not allowed, but a ruler, your ID works fine enough. And so we're going to go ahead and start drawing our free body diagram. We start with probably everyone's favorite force, the force due to gravity, or the weight. Now I'm going to go ahead and just draw it this long. Force due to gravity, okay, aka the weight. Now, at the position shown here, there's a string pulling on this block. And so we're going to draw an arrow representing the tension of the string. And the important thing here to recognize is that the vertical component of this arrow should be the same length approximately to the force due to gravity. So here, I'm going to go ahead and stretch it out a little bit further, just to where it looks like they have the same height. The vertical component of this arrow is going to be the same as the force due to gravity. Now, they're not going to get very precise on the free body diagram here. They're not going to measure it exactly, but chances are for the free body diagrams, they may have it against a grid background. And so in that instance, you're gonna want to make sure that the vertical component here supports and is equal to the force due to gravity. Now, the horizontal component of this arrow here is not too important. We don't have anything to compare it to. We just got to make sure that it points towards the center of the circle, because that's going to be providing our centripetal force here. And so that's it for the free body diagram. For these point masses, we draw the arrows pointing or starting from the center, and then they just point in the direction that they act. If this were rotation, we may want to look at the shape of the object and draw the forces exactly where they act, because we would need to consider torques, but that won't be the case here. Okay, so that's that one. Part B. Derive an expression for the block centripetal acceleration in terms of m, theta, and physical constants as appropriate. So here, as we've already have our free body diagram, we're just going to go ahead and redraw it just so that we can work with the components as needed. So I'm going to draw my force due to gravity 2 squares long, and I'm going to draw that tension up with a height of 2 squares tension. Now, before we go ahead and do Newton's second laws here, we're probably going to want to redraw this and break this bad boy up into components. And we're going to want to choose a coordinate system that fits this scenario. So I think in this case, we're going to want a coordinate system where to the left is considered positive. And that's because we usually draw towards the center, or we consider towards the center to be the positive direction of motion for circular motion problems. At the same time, we need to choose a vertical direction for positive. And we can go ahead and say up is going to be positive. Okay, so what do we do from here? Well, because our forces are not perfectly aligned with the X and Y axes here, for the tension, we're going to want to break it up into components. Now, if we remember our trigonometry, here we have our hypotenuse, and the angle is measured from vertical. This is going to make this guy hypotenuse times sine of theta because it's opposite the side. And this guy here is going to be hypotenuse cosine theta. So this is going to be a little bit of a trip up. Generally, we say that the horizontal component is the sine, the cosine, and the vertical component is the sine. But because the angle has been measured from vertical, that's going to switch things up. Okay, so what does our free body diagram become? And I'm going to go ahead and move my coordinate system. I'm going to change the color so that there's a little more contrast here. Let's see that. We're going to go ahead and move it over here. Okay. And you don't need to redraw your free body diagram. For this part of the question, they just want us to derive an expression. But it works better if we have the components laid out. Here, this will be t cosine of theta. We will have the force due to gravity acting down with an equal and opposite magnitude because this maintains a horizontal plane of motion. There is no up and down motion for this mass as it goes around in a circle. And then we have some t sine of theta. Okay, so what do? Well, we're looking at forces. We need to get an acceleration. We're going to use Newton's second law in two directions, in the x direction and in the y direction. I made a mistake here. It should be the x direction. I really dislike that about myself. It's like I'm always thinking too far ahead and not really focused on what I'm writing or saying. So I like merge the two thought processes at once. So how many forces do we have acting in the x direction? Well, we just have t sine of theta. And even though it points to the left, we can say that to the left is positive. So we don't have to worry about any negatives here in our directions. And in the y direction, well, we're going to have two forces. And we said up is positive, so we get t cosine of theta minus the force due to gravity equals m times a. Now, what do we do here? Well, now we got to think about, well, what are these accelerations going to be in this problem? Because in the vertical direction, we said that this thing maintains a horizontal plane of motion. So the vertical acceleration here is going to be 0. And that's going to make a nice little expression. We get t cosine of theta is going to be equal to the weight. The vertical component of this rope equals the weight. And that's what we were saying earlier. We'll go ahead and hold off here on this guy. Let's go ahead and take a look at this scenario here in the horizontal direction. Well, in the horizontal direction, oh, sorry. In the horizontal direction, I'm gonna have to edit that out somehow. In my video editing, like I'm using the most basic Windows editor, and the editing audio is really tedious. So for t sine theta here, the acceleration is going to be the centripetal acceleration. And that's because in this direction, that is what is causing us to move in a circular fashion. It points towards the center, and the centripetal acceleration always points towards the center of the path. It's what moves us and changes the direction of our velocity vector. So we can go ahead and say t sine of theta equals mv squared over r, and that's because the centripetal acceleration is v squared divided by r. Now, if we look at our answer or our question here, our answer does not completely satisfy the situation. They want the expression for the centripetal acceleration in terms of m, theta, and physical constant, which means that we are kind of missing some quantities here. As a matter of fact, we could even just leave the centripetal acceleration AC like this. We don't even need to expand it with the v squared over r here. We can just leave it at that. So we're almost there. And the last thing we need to do is we need to get rid of this tension because they don't want it showing up in our answer. Well, the easiest thing to do is to solve for tension in one direction and then substitute it into the other direction's equation. Now, because we want the centripetal acceleration to show up in our answer, the easiest thing to do will be to solve this other equation on the right for the tension. And so we get the tension is the force due to gravity all over cosine of theta. And we're going to go ahead and substitute that in for t in a second. Let me just rearrange this so it's a little bit more centered underneath. There we go. And now that we have an expression for t, we're going to substitute it in. So combining these two equations and substituting in with t, or for t, we get the force due to gravity over cosine of theta. And you may be wondering, well, they don't really want the force due to gravity in our answer. Just hold on. We're going to expand that bad boy. So force due to gravity over cosine of theta is going to be equal to m times a, and I'm forgetting a part here, times sine of theta, because we did substitute in for t. And hopefully you see that we have a sine over cosine. That's a nice little trig identity right there. So the force due to gravity, as we should hopefully remember, is the mass times the gravitational field strength, or acceleration due to gravity. And so we get m times g times sine of theta all over cosine of theta equals m times ac. And the neat thing here is, well, the mass cancels out. The acceleration here does not depend on the mass, it just depends on the geometry of the problem. And we can go ahead and simplify things a little bit better. And we get g tangent of theta is the centripetal acceleration. And there we go. Go ahead and look at the next part. Using the experimental apparatus shown above and the available equipment, design an experimental procedure the student could use to estimate the acceleration due to gravity at the surface of the Earth. So we're basically going to be trying to set up a scenario where we calculate or get that value. I wonder if we can use yellow. Yeah, it's going to show up as well. That's the bad dark mode on, which is fine. Well, if we look at this, we have AC, tangent, and theta. This could almost be seen as like y equals mx. So at some point, we're probably going to need to graph data and linearize it so that we can get some information for the slope, and then the slope will help us get the acceleration due to gravity. So what are some quantities to be measured? Well, here in the table below, we're going to list quantities and the associated symbols that could be measured in the experiment and the equipment used to measure them. Also list the equipment that would be used to measure each quantity. We don't need to fill in every row. If we need additional rows, we may add them in the space below. So what are some things we can measure? Well, the acceleration here is not something that we can measure exactly, but we can say v squared over r, that is the centripetal acceleration, is g tangent of theta. So how are we going to get this velocity? Well, if it's moving around in a uniform circular fashion, the velocity is going to be 2 pi r over t, the circumference of that path divided by the time. So it looks to me like we need to measure the radius. And so they're using capital R, so we'll go ahead and say r. So it'll be the radius of the circular path. And it's not going to fit here, so I'll just put radius. And then the symbol we will use is r, and we're going to measure that with a meter stick. What else do we need? Well, we need the time. Time to complete an orbit or a cycle here, and that's going to be lowercase t. And how are we going to measure that? Well, with a stopwatch. Yeah, well, what else? What else can we get? Well, we can measure the radius. Now we're wondering, how are we going to get theta? Well, there's a couple of ways we can go about it. We can use a protractor to measure the angle from vertical, but measuring angles a little tedious and difficult, especially if this thing is moving around in a circle. You could do it, and I'm sure they wouldn't dock you for it. But we can also use geometry here, because in this case, if we know the radius of the circle and we know the length of the string, then we can get the angle. This theta here is going to involve sine of the opposite over the hypotenuse. And so that's going to be arctangent, sorry, not arctangent, arcsine. So we could get the angle by knowing the geometry of the circle. Of R over L. So I would say the length of the string. And again with a meter stick. So we could approximate the acceleration due to gravity with just a meter stick and a stopwatch. We could probably just drop it and measure the time it took it to fall a set height. But in this case, we're doing it with circular motion. All right. And if you really wanted to, you could measure the angle with a protractor. Let's grab an experimental procedure to estimate the acceleration due to gravity at the surface using the apparatus. Give enough details so that another student could replicate the experiment as needed. Include a diagram of the experimental setup. Assume the equipment usually found in high school physics laboratories is available. So here, to save ourselves a little bit of time, I'm just going to say you could copy this experimental setup and put it right here. And so what are we going to do? So I'm going to assume that this motor can be varied in its strength. So we could use, like a very low speed setting, get motion for that and crank up the speed setting as need be. So let's go ahead and say, well, we don't really need the mass here as we saw. So we're not going to measure the mass with a scale, but we could if we wanted to. Well, let's see here. We can go ahead and measure the length of the string. With a meter stick. We can set the motor to a set value. Okay, then let the motor spin and then start the motor. And measure the time. And measure the time it takes the mass to complete. And so from here, we could do it one of two ways. We can measure the time for one revolution, but that can include some error. Now, they didn't tell us how we would minimize the error here, so we don't necessarily need to provide it, but we'll go ahead and say to complete a set number of revolutions and get the average time for one revolution. Okay, what else could we do? Well, we need to measure the radius of the circle. In addition, measure the radius of the circular path. And then we're probably going to want to repeat for different settings of the motor and get the time and radius each file. So something along those lines. Okay, part C. The student wants to analyze the data or data collected from the experiment by creating a linear graph that can be used to estimate the acceleration due to gravity at the surface of the Earth. State what quantity should be plotted on the horizontal axis and what quantity should be plotted on the vertical axis to produce a linear graph. So as we saw, v squared over r equals g tangent theta. So we're going to want to create some kind of linear graph out of this. Now, in our trials here, maybe we should probably also include calculate the, so at some point we probably would also calculate the angle the spring makes with the vertical. Makes with the vertical using, well, the theta is sine inverse or arcsine of r over L. Okay, so what are we going to plot in which direction or on which axis? So I think here, this could behave like y equals m times x. So to answer the question, I think on the horizontal axis, we're going to want to plot tangent of theta. And then on the vertical axis, v squared over r. Indicate which feature of the graph could be used to determine g. So if v squared over r equals g tangent theta, then b will be the slope slash constant of proportionality between v squared over r versus tangent of theta. And I think that's it for this one. Now, if we wanted to, we could be a little bit probably more precise out of this. Again, we didn't really mention how v would be calculated specifically, but we could say v squared would be 2 pi r over t, or v, sorry, would be 2 pi over t. V squared would be 2 pi r over t, quantity squared. And so that becomes 4 pi squared r squared over t. And then when we divide it by r, v squared over r is 4 pi squared r over t squared. Sorry. And so we look at the units here. That's going to be meters per second squared. We have the correct kind of dimensionality for our expression here. Should be units of acceleration. So if we wanted to, for the vertical axis, we might be able to plot it as 4 pi squared r over d squared. But either way, it's fine, as long as we kind of explain that part. Okay, so let's go ahead and look at how the College Board would have awarded points in this scenario. So for part A, section 1 point was earned for drawing a downward force due to gravity, and 1 point is earned for drawing a tension force directed along the string. The next part 2. So 1 point is earned for correctly applying Newton's second law to the horizontal and vertical forces, and then 1 point was for combining the two equations to express the centripetal acceleration in terms of the angle theta. So in the y direction, we have the vertical component of the tension minus the force due to gravity is the vertical acceleration times the mass, which is going to be 0 on the right hand side. And so we could say that the tensile force times cosine theta equals the weight. In the horizontal direction, that's where we have the horizontal component of the tension, which is Ft sine theta, or T sine theta, equals MAC, the centripetal acceleration. And again, they solve for the tension by taking the weight and dividing it by cosine theta, and then they substituted that in for the tensile force in the horizontal direction. It gave us B tangent theta when the mass is canceled. Let's go ahead and look at the next part, part B. So here's where we had to measure some quantities, and so 1 point is for listing relevant and appropriate quantities and equipment. So length of the string, radius of the circular path, time for the block to make a revolution. Okay, where's part B2? B2, B2. I don't think I have part B2 here. Let's see one. Let me go back to the AP contra and then just copy it over real quick. So, yeah, I think this is the, let me just post this over here actually. So for part B2, 1 point was earned for stating a plausible method to use the apparatus to estimate G. 1 point is earned for measuring quantities that can be used to determine the tangential speed. And then 1 point is earned for measuring the quantities that can be used to determine theta and R. Note that the relationship sine of theta is R over L should be used. And then is 1 point is earned for an attempt to reduce experimental uncertainty. And so the speed of the motor should be set so that the object revolves around its circular path at a constant tangential speed. Ooh, I did not mention the constant tangential speed. That's a key part. I just kind of assumed if you set the motor, it's going to have the same output, and so the speed won't vary. A stopwatch can be used to measure the time it takes the object to make one complete revolution around its circular path, and the meter stick can be used to measure both the radius of the circular path and the length of the string. The angle can be found by relating the radius of the circular path and the length of the string with the sine of the angle. Alternatively, the angle may be measured from the vertical by filming the experiment and by using a slow motion camera and using a protractor to measure the angle from the vertical in the camera images. And then the procedure can be repeated for 5 different tangential speeds that can cover as wide a range as possible using the available equipment. In part C, they said vertical axis would be tangent of theta and horizontal axis would be r squared r over t squared. We have it a little bit different. We were saying on the horizontal axis we have tangent theta, and they're putting it on the vertical axis. Not a big deal. In their approach, if they go ahead and say that part, then G is going to be we're going to get it some other way. So like for instance, let's go ahead and say we had 4 pi squared r over t squared equals the tangent of theta. And we said that this is going to behave like y. If this behaves like y, we need to move over the G. We're going to move it over by division. So this expression starts to become tangent of theta equals 4 pi squared over G. and then r over t squared. And so this is the stuff that will be changing with each trial. So let's group it together. That's going to be changing during the trial. That's going to be changing during the trial. So then what this gives us here is 4 pi squared over g. This would be the slope of tangent theta versus r over t squared. So either one is fine, not a big deal. In our approach, we were saying that if anything, g versus, I'm sorry, v squared over r versus tangent theta would, the slope of that would give us g. Neither one would work. Part 2c, 1 point is earned for giving an appropriate feature of the graph that could be used to determine g. So they say the centripetal acceleration is this, substituting the expression 2 pi r over t for v gives us this equation, and the slope of the graph tangent theta as a function of r over t squared can be used to determine g. So here they're being a little sloppy. They're not completely explaining that it would be the constants all multiplied and divided by g would give us the slope. So that's kind of where they're just kind of like being a little general, but either way, it's fine. Let's go ahead and take a look at question number 2. So we have 3 different planet-star systems which are far apart from one another. So these systems are not going to interact with each other gravitationally. The masses of the planets are much less than the masses of the stars. In system A, planet A with a mass MP orbits a star A with a mass ms in a circular orbit of radius r. In system B, planet B of mass 4 MP orbits star B of mass ms in a circular orbit of radius r. In system C, planet C of mass MP orbits star C of mass 4 ms in a circular orbit of radius r. So for question A, they ask, the gravitational force exerted on planet A by star A has a magnitude F original or F naught. Determine the magnitudes of the gravitational forces exerted on systems B and system C. Okay, so let's go ahead and see here. So here they're testing our understanding of Newton's law of universal gravitation. And so the force due to gravity between the star and the planet, if you will, is going to be big G, mass of the star times mass of the planet, all over the distance between them squared. So let's go ahead and see here for system B. I'm going to go ahead and work down here. So the mass of the star is just ms, or really m1 and m2, right? Like we usually write it as m1 and m2, but not a big deal. Okay. The mass of planet B, or the mass of planet, is going to be 4 mass of the planet. You know what? Let's go ahead and say planet B. I'll put a little b subscript here. And the distance between them, the distance between B and the planet is going to just be off. Okay, so we throw this all together and we get that the force in the system B is going to be big G times 4 mass of the planet times the mass of the star. And it doesn't matter who we write down first. I mean, if we wanted to be super precise here, we should have put the stars first, but I wrote a 4 because I was getting ahead of myself again. And just to remember, the order of multiplication doesn't really matter for these scalar quantities. And so then what's the distance between them? R squared. Okay, so we get the force in B is going to be 4g, mass of the planet, mass of the star, all over R squared. Okay. And so we're going to eventually need to compare that magnitude to the magnitude of in system B and system C. Let's go ahead and look at system C. System C the mass of the star in C happens to be 4 times the mass of the star, ms. The mass of planet planet C is going to be the mass of the planet MP. And then the distance between them is going to be R. So we put this all together, and the force due to gravity in system C is going to be big G, 4 times the mass of the star times the mass of the planet. Oops, let's go ahead and scroll over to the side of it. All over R squared. And so we get the same thing here. G 4ms. We actually write it like in system B. 4 times G times mass of the planet times mass of the star all over R squared. Okay. Let's go ahead and compare that to system A. So in system A, well, we just had a mass M, and R. So the force due to gravity in system A is going to be big G, mass of the planet, mass of the star, all over R squared. So these guys pretty much all have the same thing, except for, for systems. With systems B and C, there's a multiple of a 4 in there. Oh, come on, man. Please, cursor. Don't have me curse you out. But there we go. We're able to see it now. So what we can say here is the magnitude is going to be 4FO and 4FO. And that's a little thing. Let's go ahead and change that to green. A little thicker and a little bit more noticeable. So it's going to be just 4 times as much. All right. The next part is, how do the tangential speeds compare to that for planets B and C? How do they compare to planet A? And so in a clear, coherent paragraph length response that may contain equations or drawings, provide claims about why the tangential speed of planet B is greater than, less than, or the same as that of planet A, and why the tangential speed of planet C is greater than, less than, or the same as that of planet A. Okay, so let's go ahead and start thinking about what's going on here. Well, the force due to gravity is going to be the centripetal force. Force due to gravity points towards the center, and it is the only force in the system, and that's what's going to cause the planet to go around in a circular orbit. And so we have learned that the force due to gravity is big G, mass of the planet, mass of the star, all over R squared. And the centripetal force is going to be the mass of the thing going around in a circular path. In mv squared over r, it's the mass moving in a circle, which is going to be the mass of the planet. And then here would be v squared over r, where v is the tangential speed. So we're going to be looking for that. So what do we find out? Well, as usual, the mass of the planet does not matter. And we start to get an expression like this. So we get, well, r is going to cancel one of those exponents, because on the bottom of on the left side, we have r times r. And then when I move one of the r's over, that's going to cancel it. And we get that v is going to be given by square root of g times the mass of the star that they orbit over their distance. So let's go ahead and start taking some inventory. Well, the mass of the star in systems A and B, so the mass of star A is ms, the mass of B is ms, but the mass of star C is going to be 4ms. So the speed here does not really matter on the mass of the planets. It really just depends on the central star here. Okay. Now let's go ahead and talk about the radius. Well, the radius of A is just r. The radius of B is just r. And again, radius here is the orbital radius, the distance from the center to where the object is. And then the same thing for this guy. I shouldn't do that. Okay. So what does this tell us? The velocities of A and the velocity of B are the same magnitude because their masses and their distances from their stars are the same, or the masses of their stars, to be more precise. And then the velocity of C is going to be approximately 4 times, not 4 times, 2 times, because we need a square root. It's going to be 2 times the velocity of A and 2 times the velocity of B by that analogy here. Or not analogy, but equivalence. Okay, so what can we say? So planets A and B have orbits of the same size what do we mean by that? R and orbit R's equivalent mass the tangential speed of planet B is the same as the same as the tangential speed of planet A. And planet C orbits a star with 4 times the mass. Equivalent distance as planets A and B. It will experience or have a greater tangent. To be precise, it would be 2 times bigger. I think that does it for today. Thank you for watching, and hopefully this made sense. Be sure to stop by if you have any questions. Have a good day, y'all.